Okay, everybody, welcome to Operating Systems on our lovely Monday. And we are in the middle of the term, and so we're hitting a topic called main memory, which is chapter 8. If we could hold down the talk a little bit. I'm trying to lecture here. I'll just give it a few minutes. Okay. So this is main memory, which is chapter 8, and it is also a very important concept. So what I'm going to talk about today is the background of memory, how memory is used on the operating system and on the computer itself, the concept of swapping, the concept of continuous memory allocation, paging, the structure of a page table, segmentation, and then talk a little bit about the Intel platform in terms of how memory is implemented. So memory is how things are running on the computer. Okay, I don't want to compete with you guys anymore. I'm going to stop talking until you guys stop talking. Okay. All right, now I don't have to feel like I have to yell over you. Okay, so the objectives is because, well, some of you guys who weren't paying attention, we're talking about memory today, chapter 8. Now that you're on the same page. What we want to do is provide a let's start talking again. Are we ready? Okay. I'm going to hopefully be able to eventually here provide you with a detailed description of the various different types of memory and how it's organized on the computer. And also discussing various memory management techniques, including paging and segmentation, and then providing a detailed description of how it's implemented. So without memory, nothing is going to run on the computer. So the process itself is a memory abstraction. So we create a process, and the process is scheduled by the CPU scheduler. And we have allocated resources for that process, and the main resource is memory. So we have a memory location that's set up where we're loading the program code that the process contains, along with a stack and a runtime, the runtime engine essentially, which is being facilitating the running of the process from a memory location. So a program must be brought from a disk into memory and placed into the memory itself. So within the process for it's going to be run, into the memory and placed within a process for it to be run. Well, the process is the abstraction of the program and the instructions that it needs in order to execute and run. The memory is the holding place for it. So the memory is not necessarily providing any runtime support or doing anything. It's just a holding ground. It's like a temporary waiting spot. And the process itself is being kept track of in what's called a process control block. It's a data structure that the kernel is keeping track of to organize how many processes are out there. One of the main components of that process control block is a memory address. And the memory address is where in memory is this process residing, so that we can essentially keep track of what's going on with it and manage it separately. Processes don't share memory with other processes, and we have inter-process communication that goes on where we can do shared memory, and that's memory that's held by the kernel and managed by the kernel. So main memory and registers are only storage for CPU, and they can be accessed by the CPU directly. So we don't really talk about processes using registers, but the registers are being used by the CPU scheduler and by the kernel to keep track of which instruction is being executed, what data value is assigned to each variable, and all sorts of different useful information from a processing perspective. So imagine that the CPU is the center of all of the activity. The farther we get away from the CPU, the bigger the memory gets and the more less expensive it is. So closer to the CPU, that memory is more expensive. I mean, it costs more to buy it, actually, and it's smaller. So the memory used for registers is extremely expensive, and it's very small. And then cache would come next in the kind of the breakdown. And cache memory is a little bit bigger, 256, 512. That's pretty big, actually, for cache. That's used by the CPU scheduler and the kernel to keep track of instructions so that we don't actually have to move it back to main memory. By the time we get to our main memory, we've gotten a lot bigger. We've gotten to 2, 4, 6 gigs, 8 gigs of RAM out there. More expensive. Less expensive. and bigger, much bigger. And then we have the hard drive. The hard drive can actually be used as memory as well. So we always think of hard drives as secondary memory, but we have this thing called a backing store where we can actually use the hard drive as main memory. So then the hard drive, everyone knows, are really cheap actually, and they're really big. We're talking about 300 gigabytes or 600 gigabytes or so, or terabytes or so. So main memory is what's in between everything, and main memory is what's used to hold track of the processes. So registers accesses one CPU clock or less, so the speed of the access time for a register is extremely fast. The speed for cache is second to extremely fast, so it's faster, but not as fast as the registers. Main memory is slower than that. The hard drive space, secondary, is very slow compared to that. So we want to load things up as close as possible and then move them farther away, move items farther away when we need more space up close. And in a perfect world, everything would run and get out of memory. We don't want to keep things around in memory. Unfortunately, that's not how computers are used these days. It's not how the Windows works, not how Mac works. Instead, we have multiple programs that are loaded up simultaneously. They're all residing in memory, and nothing goes away. So we're kind of fighting against the system with the user experience, so to speak. So main memory can take many cycles compared to one clock tick per CPU cycle in the beginning. So cache sits in between the main memory and the CPU registers, and then protection for memory is required to ensure correct operation. So we have these areas are protected so that each process is able to keep track of what it's using, and the CPU can keep track of it, and other processes won't corrupt it. So we take this kind of shared environment, and then we make it so it's not shared anymore. We make it so that's only one process is using a particular part of the resource at one time, and that guarantees us cooperating processes for the most part. So here's a base and a limit with registers. A pair of base and limit registers define the logical address space. So we have this thing called physical memory, logical memory, and then virtual memory, or main memory, so to speak. So physical memory, that's the easy thing. You go to Fry's and you buy it. They're boards, and you stick the physical memory on the computer. And the physical memory gets wired into an MMU, memory management unit. The operating system reads from the MMU, creates logical memory from that. The logical memory is the abstraction of the base and the limit, because we're not going to read the physical addresses. If we read the physical addresses, well, not only would it be too slow, but how are we going to know what they are? Everybody out there makes memory. We have different manufacturers for memory. Not everybody uses the same addressing scheme, nor do they use the same chip size, nor is it configured all the same way. Well, the MMU tries to put it together. When you buy memory, you're buying it for the MMU. So if the MMU says, well, I can hold up to 4 gigs, even though you can stick 8 gigs on it, MMU is only going to hold 4. It's only going to store 4, or show 4, for example. And it only runs at a certain speed that the MMU is configured for as well. So lo and behold, it's better actually to buy memory that matches the MMU than it is to go higher or lower than that spec. Because what you want to do is make the physical part work with the memory management unit, because the memory management unit is controlling everything that is associated with the abstraction of what's there, what exists. So it doesn't really matter what's physically there. The MMU is going to tell us that. So, which is kind of an interesting phenomenon. People always run into that situation when they go buy memory. Because how do you know what kind of memory, well, whatever's in sale, right, or whatever's in the store, and then the salesperson will always sell you on the faster RAM. It makes no sense. If you put faster RAM in there, it's not going to work. Well, it will work, but it's not going to give you a faster speed. You might as well buy the slower stuff. But the unfortunate thing is the slower stuff now is more expensive than the faster stuff. Because people, the newest, the latest and greatest comes out, and then you have a low supply, nobody's making the slower speed memory anymore. So, long story short, it's always a confusing shopping experience for most people who go out and buy memory. And then if you're buying it for an Apple, but there's certain brands that actually support the configuration a little bit better. You'll get better performance out of that. So that's why memory itself has different prices associated with the same thing. You can have 2 chips, 1 chip. Configurations are different depending upon how it's configured. long story short, not all memory is the same. So, and you want to buy what's good for your MMU. So check the stats on your computer. Don't buy anything higher than what you actually need. Because actually, in some cases, it can make the computer run hotter, you know, because it overclocks the memory is running at a faster speed than the MMU can handle. So it will actually wear out your computer a little bit faster if you have a notebook computer, actually. So let's see. So we have this abstraction of the base and the limit registers. And here we have the process 1, process 2, process 3. Basically, just think of this as a starting and an ending address. We're going to start here. We're going to go for so long. All processes get allocated the same amount of memory, and each operating system sets that before the process actually even starts. So each process gets loaded up into memory. It's always the same in terms of what size memory space they're going to get. So binding of instructions and data to memory. So all of those things that we're doing in a programming language like integer I and float f and all these other things is creating data and creating essentially storage and data in memory. So long story short, somebody had to define what int meant and float meant, and this is really referred to as static memory allocation or static memory binding, which means we're going to take a memory address and we're going to call it I. So in a programming language, we use something like integer I and we call it a named variable that has an identifier. Well, that's I, or integer, I is the name of the variable I created. That will get loaded in the data section of your memory process when that gets loaded up. And then people go, oh, what about C++ and pointers? That's good. So what you're doing is you're allocating in the heap section of that process space, all in the same process space that you're allocated for the process. And then you're working with the address instead of the identifier. Well, isn't it really the same thing? Yeah, kinda. You just have a little bit more control over it from a memory management perspective. So address bindings of instructions and data to memory address can happen in 3 different stages. So we have compile time, load time, and execution time. So static data is done at compile time. Static data is using a predefined type in the language, like int or float or double, and then assigning it, making a variable. Every time you make a variable, whether it be an array or a variable, whatever it happens to be, is static. So at compile time. So if memory location is known, then the absolute code can be generated. Must recompile the code if starting location changes. So if you're going to change the concept of integer I and make it float I, you have to recompile the program. Well, you have to change the data type, which is going to change how much space is actually allocated for that variable. And it's going to change the binding, so you have to recompile the program in order to change it. You can't make an integer I and then out in runtime while the program's running, treat it like a float. You'll get a type mismatch error. Actually, the program won't even compile for you if it's C or C++. So that's really what's meant by compile time. Important to note because then it's the compiler that's coming up with the configuration and the allocation technique. Eventually your C code gets translated into assembly language, and you have the assembly instruction that is giving you how much memory that you need and what kind of memory, and how's it going to be formed, what it's going to be used for, kind of thing, which is going to be the implementation details when it gets converted to assembly language. And then we have load time. So load time must generate relocatable code. So if memory location is not known at compile time, well, it's not known. It's kind of like pointers. So pointer is a load time, and it's used in the heap memory. So if we don't have to, if we know ahead of time what's going to go on, then we can load it in the stack, from the stack on a compile time, and it can go in the data section, which is the lower part, and it can actually run faster because it's in the lower part of the memory banks. Imagine this as a search space problem. We start at 0 and we go to 200. Well, if it's down here at 1 or 2 on the bottom, we're going to find it faster. If we have to go through all 200 banks or something to find this thing, it's going to take longer. So if we take and do load time, we're going to load it at the heap, which is the highest memory location. Static time gets loaded at the lower, the data section on the bottom of the process space. And then eventually what's going to end up happening is you're going to figure out, well, all right, every time I run this program, Sometimes it works and sometimes it doesn't work. Well, that's what you get with heap memory, because it's not allocated until load time when everything is loaded up for the running process. So it may not necessarily might not necessarily be located in the same location. We might run out of memory. Something might happen. It's kind of, for the most part, a little bit less reliable than a compile time, because we can't air check it either. Until we load it up, we don't know if it's really going to work or not for us. And then we have execution time. So execution time is the binding delay. So we delay the binding until runtime if the process can be moved during its execution from one memory location or one segment to another. And so you need hardware support for address mapping based on limit registers if you're going to do it from execution time. Well, Java sort of has load and execution binding. So we have binding that occurs with the memory. So the word binding is associated with memory. So unlike other terms like allocation, allocation is reserving the memory, stamping it with an identifier. Binding is going to basically say that this is the memory address that's associated with this piece of data that we're using. And the data could be a variable, it could be an object, it could be a class file, it could be anything. And all acts the same way in terms of its definition. So if we wanted to, we could create a language like Java as an example and do everything runtime or load time. And then we call that a dynamically bound language, which means until the object actually gets loaded, it's not going to get loaded till runtime, we're not going to know where it's at. So what Java does is it loads up a class module and puts it up in the memory, and then basically records a memory address for that class module and says, okay, at 0x5551212 or whatever, we have, you know, main.class, and so, or I don't know, person.class or something. And so then every time the code actually looks for person, it goes, and it's bound to that memory address, so it goes to the memory address. So you don't have to keep loading it up over and over again. So that makes the execution time and load time run much faster. Because in a compile time configuration, yes, everything is loaded down low, and it's faster, more easily accessible. But every time you run it, you have to reload it. Because it's compile time, it's not dynamically allocated, it's statically allocated. It's like starting all over again every time you run it. In a Java program, you run it once, you load it up in the memory once, you bind it once, and then you just link to it over and over again. Because there's static time binding and linking, dynamic time binding and linking that happens in that language. I'm talking about Java because it's an operating system in itself. The JVM is what's managing this versus a Windows operating system. A Windows operating system is going to do it compile time. That's why we have Visual Studio, and we have exe files and com files, and those are statically allocated compile time executions that work at a static allocator with a static runtime, which is what we get with Windows. We also get the same thing on the Mac. It's not just a Windows thing. But if we load Java on top of a Mac or Java on top of a Windows machine, then we have everything dynamic. It's actually kind of confusing because it's not 100% dynamic. Some people call Java a hybrid language because it's partly compiled, partly runtime. Because some of the code is compiled, some of the binding is compile time, and then most of it is execution time or load time. Because when you create that .class file, you are at compile time creating intermediate code that contains binding, and that binding can be used at runtime. So it's like a hybrid. Half of it's bound at runtime, half of it's bound at compile time. So multi-step processing of a user program. If we think of the concept, we have the source program. Well, that's your lines of code, your integer I and your float f and everything. And then we have the compiler or the assembler. This is compile time, really. Anything that happens in this stage, and then we get a .o file or an obj file that comes out of it. It's an object that can be linked. And then we go through a linking stage. So in the old days, for running GCC, you'd had a make file. And you'd come up with, I want this file, and this file are going to come into these objects, and then link these objects and these objects together. So you compiled, and then you linked, and then that created the .exe file, which everything all was put together for you. The linking stage just puts it together, combines all the object code together. So if you have a compile time configuration, you have to combine it together, because when you double click on that file to load it up into memory, and this is what we're talking about today, is the memory component of this, it needs everything, and it loads everything up into the memory. Well, that's a little bit different than if it needs to decide at runtime what it's going to load. So Java, it takes and goes up to here. We get object code. What do we get? .class files. If you've ever compiled a Java program, you notice you have like 5 or 6 different .class files, and people always wonder, well, how do we get this thing to run? Well, you run main.class or whatever you called your driver program, and it loads all your other objects. And then if you have other programs out there that are also using those objects that are loaded up there, well, then you don't have to reload them. It just essentially links to it dynamically. So you only have one person, one employee, one staff, or whatever you have these objects created at, loaded up into memory, and you're dynamically binding and dynamically linking all those components together. Well, it gives you a faster execution time. So the interesting thing is, because everything's delayed on Java, people think, oh, Java runs slower, but it doesn't. It runs faster. It runs slower in the beginning, and then the execution of it runs faster, versus a C, C++ environment that runs faster in the beginning, but the whole program runs slower in the long run. Because every time you need something, load it up into memory, take it out of memory, load it up into memory, take it out of memory, load it up into memory, take it out of, over and over again. Well, throughout the life of that program, if you put them two together and compare C++ with Java, Java's going to run faster. You only load it once, leave it up there. And if you need more room, take the garbage collector comes around, takes something out. It's a lazy collector, so it's not going to work. It's not going to take up overhead unless it needs space. If it needs space, okay, make some space, and then put it back eventually. The C++ program, every time you run it, it's a brand new environment, and every program you run has got to have duplicate objects loaded up. So it's wasteful in terms of how much memory it's occupying, and it runs slower. Although it starts up faster, because it's all together. There's nothing that has to happen at runtime. It's all statically bound, already pre-configured for you. All the objects are included right there, so it doesn't have to go out and look for them. You just load it up, which is kind of interesting. So you can take a C program and make it Java-like by using DLLs. So DLLs are dynamically linked libraries. So it's object code at this stage that's not linked into the .exe file. Instead, it's turned into a .dll, and it's loaded into a shared directory on the system. So now when the compiled program loads up, everything that was statically bound is now dynamically executed, dynamically linked. You're delaying some of it until runtime. You're making it more Java-like. And then you're conserving memory. You're not using as much memory as you were before, because you only have one DLL out there, and then you can link to DLLs that are part of the operating system or that are part of third-party libraries and stuff out there without having to compile it into your code. Then you can update the DLL without having to update your executable file, which is how Java is another benefit of Java. All the class files are separate, so you don't like one has a bug in it, just replace that one file. You don't have to replace the entire program, just the object that's having the problem. Well, if you're running DLLs in Windows, you can do the same thing. So after the DLLs came around, then we're noticing faster running, more efficient programs. You build the operating system based on DLLs, which was an excellent idea, then you have faster running Windows. So around XP-ish, maybe a little bit before XP, everything went DLL on it, which is great because now the operating system runs faster, much faster than it used to run in the old days. So going back to the example here, they have the program source code gets created into object models, and then other objects get linked together. So we have a linkage editor, and then we have a load module, which is our load time. So we have a dynamic loader in Java. We have a static loader in C++. Actually, the loader is still static in C++, even with the DLLs, because it knows what it needs to load. But you can't change it at runtime, which is how if you mess up the registry, and the registry is an index for the DLLs, by the way, and for object code. It's the memory. Instead of actually going out and searching all your memory for all the little locations where everything is, we'll just predefine it, put it in a register, look at the register, look it up, and go, well, where's this code? Oh, it's over there. So it's holding, which is why you can't normally edit stuff out of the register memory locations. After the system's been running, you have to reboot for some of those changes to take effect, because a lot of that stuff is memory locations for where a module is loaded. So if you're going to link to it and you're going to create a load module or load time kind of configuration, you can statically say, hey, it needs xyz.dll. Well, you remove xyz.dll from your computer, or you edit the registry so it can't find it or it doesn't load it. Then you end up with a situation where the program's not going to run because this DLL is missing. Well, you don't have that in Java. Java, you have more dynamic loading as well because it's truly dynamically loaded. Here it's kind of makeshift because the object code could be dynamic, but the loading is still static, which is kind of interesting. We don't see a dynamic loading yet. So we have a loader. The loader is held by the runtime environment in Windows or by the JVM in Java. And then we have our dynamically loaded system libraries and linkage, dynamic linking and things that are going on. So we have in-memory binary and memory image that's being stored here. So this is the execution time or the runtime. So you can see sometimes people call this early binding, and then they call this late binding. They call that early because it happens earlier in the system. So compile time is always early. There's no word, there's no description for the middle. It's just, is it early bound or late bound? Early bound means compile time, late bound means runtime. So, because this is happening later in the system. So that's where the early and the late come from. They call it static and dynamic because static from an early binding at compile time doesn't change. It's consistent. The memory is always going to be allocated the same. Now the memory address can change. But the binding is never going to change. It's always going to happen the same way. So what's changing is the binding technique or the routine that's being used. In a dynamic, we can bind or we can't, but we don't have to bind. We can change it at runtime so that the binding doesn't always occur if we don't want it to occur, which gives us late binding, which gives us dynamic. So the words dynamic and static are kind of interesting. People think, oh, static never changes. Static can change a lot. It's the binding that never changes. It's always going to bind certain variables with certain data and locations. That will always happen. Dynamic is optional. So it all happens at runtime, yes, but technically the binding may or may not occur unless it's needed. So if it's dynamic, then unless we need it, don't run it. So if you do a dynamically bound language, like a dynamically linked and dynamically bound language like Java, you don't need something, don't load it up into memory. The program call needs it, load it up into memory. C is statically bound because it's going to be loaded up into memory whether you're going to use it or not. So what ends up happening in a C compilation program is the compiler will check and see, you know, we've defined this variable but we've never used it. And it'll come back and it'll tell you, hey, you didn't use this thing. And you'd be wondering, well, what does it matter to you? Well, it's going to statically bind it and allocate it, which means you're going to take up resources and you're not even using these resources. Why are you doing it? It's concerned about that. It's trying to help you. In Java, oh, well, you can turn the message on, but you can suppress this as well. It doesn't care. If you did integer I, but you never used I, no problem. It's not taking up any memory. It's not going to be dynamic. It's not going to be allocated unless it's going to be used. We don't need it. We're not going to allocate it. So, which, you know, we can have a bunch of classes in the system. And that's the other thing people worry about. Oh, I've included this and I've included that. Well, the includes are a little bit different. Depends on what you're going to use. So to include something means bind the object code if the object code is going to be used. Include it in the compilation. Bind that code. Java uses import, which means bring it in, bring the whole object in, or bring in whatever we need. Don't include it. You're not including anything in the object code, but you're going to import it dynamically at runtime, which means we're using that object over there. We're not part of that object, but we're going to use it. Import this package, and this package contains these millions of objects. And then at runtime, we're going to load whatever object we need, whatever the code does. So, which is actually kind of an interesting concept. They changed the word. You know, it's purposely, an include is not equivalent to import. It's two separate concepts. And it depends on when that object code is going to be bound and linked. So let's get to the memory. Logical versus physical memory addresses. Nobody ever sees the physical addresses. You can't see it. Only the MMU sees it. MMU gives the operating system an abstraction of the physical addresses. It's generic. It's never no one's ever going to see those addressing. Why would you want to see it? It wouldn't make any sense. So the concept of the logical address space that is bound to a separate physical address space is central to the proper memory management system. So in the old days, we had a one-to-one mapping. We would take the physical address, map it to a logical address, which basically says that, you know, if we load something up into memory, we're going to logically load it up into this memory. Use whatever physical is available to you. The MMU does the mapping from logical to physical. So we're reading the logical, we're using the logical from the MMU end that's on the operating system side. We go and say, okay, put this up in the memory. MMU goes and finds the physical addresses located that is assigned to this logical space, which could be more than one address. So usually a range that says we're going to logically create this location. It's equivalent to so many, like 10 physical locations or something. So the mapping can be, you know, 1 over here to 10 over here or something, depending upon how we're going to use the memory, how we're going to configure it. And then in that particular case, then we can ask the MMU, hey, we need a space number 1, and logically to physical translation from an MMU perspective goes over and gets 1 through 10, which is identified as space number 1 from a mapping perspective. We map it because then we can make use of different memory configurations. We have a 32, a 64-bit system, which is kind of interesting. People go, well, you know, I don't know what system I have and I'm trying to install software. Well, interesting thing is it depends on how your memory is mapped. It's mapped differently in a 32 versus a 64-bit system. Your logical address spaces are different. The program's not going to run correctly. You can usually go down, but you can't go up. So you can run on a 64, you can run a 32-bit program. You're not making efficient use of your memory, half of it's empty. So you don't want to run too many 32-bit programs on your system because you've got what's called internal fragmentation, which means the code is taking up 64-bit memory locations, logical addressing, but it's only using half of it. So you have internal waste because other stuff can't use it. Only that program can use it. So that's internal fragmentation versus external fragmentation, which means, you know, not all the memory is used contiguously. We have little holes in the memory, and the operating system needs to find the holes to put the stuff into. Because only one thing can be held into memory at one particular moment of time. And we have tons of things that we're loading up. So the other reason why we map is that we can make twice as much logical as we have physical for, if we wanted to, or the other way around. So we can make our own abstraction. We make our own abstraction, then we can manage the memory, and that's what the chapter is all about, actually. It's the abstraction of the memory management concept. Because we have this thing called swapping that works as well, and we have this thing called a backing store. So if we have 20 spaces of physical memory, we can turn that into 40 logical if we wanted to, and then use the logical as some sort of a representation of some sort of a system where if, for example, we fill it up, then we can't go back to, we need the physical to run. But if we can't load it up into a physical address, then we put it on this thing called a backing store. A backing store is formatted hard drive that looks like the memory. So we take it and we swap it. So swapping takes something out of memory, puts something back into memory. It's similar to context switching. No work actually gets done. It takes CPU cycles to actually get to actually perform. But at the same time, it allows us to put more up in the memory than what we have physical room for. It's kind of like it's kind of like how you can spend more money out of your bank account by using your overdraft protection. That's like swapping. We're gonna give you some funds. We're gonna put some funds in there, and then we're gonna take some funds away. So what we're gonna do is essentially swap in some money from some other source, and then basically that's what the memory is doing. So logical addresses generated by the CPU, also referred to as virtual addresses. Virtual addresses don't exist. The only thing that really exists here is the physical address. It's the address seen by the memory management unit. So we have logical and then we have virtual. They fall into the same category. A logical is normally a one-to-one mapping where we have one address logically that's mapped to a certain number or a certain partition of the physical memory. And it's the mapping that we refer to when we look at the MMU that maps logical to physical. Virtual is let's take that and turn it into 20 more. like, let's add some memory to the system. So we can make this abstraction like we have a lot of memory. So virtual memory is an abstraction on top of logical. Creates twice as many logical addresses for you, 3 times as many. Why do you need that? Because the user wants to load everything up into memory. How are you going to keep track of everything? You need a space for it. So you have all of this virtual doesn't exist, these virtual spaces that you're loading up that are going to use the logical memory eventually, that's going to use the physical memory eventually. And you have swapping and movement of that stuff that goes back and forth. So we have caching. Caching says instead of swapping it out, let's put it locally. Because if you're going to run something often and you need that piece of information in the main memory, you don't want to swap it out, you cache it. Cache it just brings it a little bit closer to the CPU, takes it out of the main thing, makes room for other things to fit in the memory, and then makes it available locally because the CPU needs it. So we have this hierarchy of memory that runs from registers to cache to main memory to backing store. And the backing store again is just the hard drive partitioned to look like the main memory. So older systems had this thing called a swap drive. You can create a swap drive. Actually, you can do it in Windows still today. You can create a swap partition. What does that do? It makes you more. Gives you more virtual memory. Makes your backing store bigger. And they say don't make it too big, because if you make it too big, you defeat the purpose of making it big to begin with. So imagine it as a search space problem. If you take an algorithms course, what ends up happening is you figure out, well, the bigger the search space, the longer it takes to go find something that you need. So if you make it too big, it defeats the purpose of making a reserve, because it takes too long to search it. It slows down the efficiency of the algorithm. So logical and physical addresses are the same in compile time and load time binding schemes. Logical or virtual and physical differ in execution time address binding schemes. Yeah, physical addresses are allocated as a first come, first serve perhaps, or round robin, or whatever technique you're going to use, but as a dynamic allocation. Always happens at runtime. You're not going to ever reserve physical memory at compile time. Doesn't work that way, because we never know the physical address, which is actually kind of interesting, because you get the beginning C++ students will say, well, how do you know the memory address? You don't need to know the memory address of a pointer, because you're never going to know the memory address of a pointer. It's always going to change, because that physical address is never going to be allocated until the program actually runs. You know how much you're going to need. You called it init. So, which is actually kind of interesting, because when you use pointers, people go, well, how can we have to call it an integer pointer or a float pointer? We have to give it a data type. Because those data types are what's defining how much space we're going to actually take up. And depending upon how much space we're going to take up dynamically, we're going to allocate the physical and the logical to it when the programs run. So it's kind of interesting. They call it dynamic binding because it is truly dynamic. We're never going to get any memory addresses out of this, though. We're never going to see it. Although we can print it to the screen and we see it, but it doesn't mean anything really, because it's always going to change every time we run the program. So our MMU, as I mentioned before, it's the hardware device that maps the virtual or the logical to the physical address. The book has a tendency to use the word virtual instead of logical. I like to use the word logical. They're both in this context meaning the same thing, actually. It's the same abstraction. Whatever's not physical is virtual or logical. But logical is really, in my opinion, more of an MMU kind of terminology. So in the MMU scheme, the value in the relocation register is added to every address generated by the user process at the time it is sent to memory. And then the user program deals with the logical addresses. It never sees the real physical addresses. So I always think of logical, because that's what we're seeing. We're seeing what's coming from the MMU. We're not seeing what's coming from the physical allocation. So here's a dynamic relocation using a relocation register, which means put it into memory at a location. It's a relocation because it's not the logical address, it's the physical address where we're trying to locate it. So here's our CPU on one side. Then we have our logical address. Oh, let's put it in 346. What does that mean? We have no idea. We have to do the mapping. So we go to the MMU, where we have an algorithm that determines where it's going to be located in memory, depending upon the addressing scheme that you use, because this is divided out into these logical addresses. So our MMU does the mapping at 6 and says, well, we're at really 14346. That's the equivalence. So we take it over here, which is actually kind of interesting because this address here might end up different over here depending upon your relocation algorithm and depending upon how your MMU is mapping it. We want to make better resources here. So if we keep using the same memory address all over and over again, it keeps mapping it. The whole thing is empty except for this one little memory address up here. Oh, I think we have attendance. Hold that thought. Okay, I'm back. We're going to continue here. Yoo-hoo! We're going to continue. So I was talking about, it was a really bad break actually because I can't remember what I was talking about, but it was logical address to physical address mapping and how the addressing may not necessarily always map to the same physical address because what we end up having is too many logicals that don't match one-to-one to the physical. And if that's the case, we're talking about the virtual memory. The virtual memory is an abstraction of the logical, sometimes called the same thing. We go through this relocation register that's part of the MMU. This is a hardware component. It's going to do the mapping for us. So if you want to think of it, because lots of students immediately come up with this, well, what's the difference between logical, virtual, and hardware, or physical? Physical is the only thing that really exists. It's hardware. It's logical is the mapping, virtual is the mapping. Could be mapping to the physical, could be mapping to the logical. It acts just like logical because it doesn't exist. It's an abstraction on top of the virtual. But usually, on top of the logical. Usually virtual memory is an abstraction on top of logical though. It's not, it could be, but it doesn't normally be an abstraction on top of physical. We usually refer to the logical address, and then we have virtual addresses that refer to logical addresses. So if you want to think of the hierarchy, it goes physical is closest to the memory, logical is closest to the MMU, virtual is closest to the operating system data structure that's being used to keep track of the memory. So in dynamic loading, the runtime is not loaded until it's called, and we have better management, better memory. As I mentioned before, I talked a little bit about the runtime actually before. Then dynamic memory is always allocated a lot faster. So better, because if it's loaded, we don't have to load it again and again. So it makes more efficient use of the memory. Better memory space utilization. Unused routine is never loaded. And then if it is loaded, it's at the same location. Well, the routine is loaded just once and it's kept there. And then we just refer to that memory address over and over again. And it's useful when we have large amounts of code that are needed to handle infrequently occurring cases. Because if it doesn't occur, we don't have to load it. And then no special support from the operating system is required to implement through the program design. We just use what's there for us. In terms of dynamic linking, so this was dynamic loading, by the way. In terms of dynamic linking, the linkage is postponed until execution time. So to load it means to bring it up into memory. To link it means to associate the memory address with the program code so that we can use it. We can call back and forth. So linkage is postponed until execution time if it's done dynamically. So that's a small piece of code or a stub that's used to locate the appropriate memory resident library function. And the stub replaces itself with the address of the routine, and then it executes the routine. And then operating system is needed to check if the routine is in the process's memory. If not, it has to be loaded. So this is where we get problems with the dynamically linked libraries in the register. When the loading occurs, the registry is updated with the memory address for where the loaded module or loaded DLL file, the object code, is actually residing. We dynamically link it within the source code to go to that memory address. We go to that registry, we look it up, and it'll say, sorry, it's not here. It's not loaded. Well, it doesn't mean that we didn't load it. We could have loaded it, but maybe the registry was corrupted. The registry didn't get updated, so it's there, but we can't find it. But for the most part, people edit the registry and they take away the linkage, and then they remove it, and then we needed it. And then that ends up with a problem. So long story short, never edit your registry because then you're going to mess up memory locations where these objects are. And lo and behold, you may have needed the object that you thought you didn't need to be essentially loaded. So the stub is another word for that for a placeholder. It replaces itself with the address of the routine and executes the routine. So in a Windows environment, we talk about the registry. In Java for RMI, we talk about stubs. So the same concept actually exists in Java, where we have remote method invocation, where we've loaded objects up, and then we have an RMI manager that looks at a stub. And stub is basically sort of like a registry. It's a lookup technique that shows you an index of loaded code and which machine it's at and what's available. And it goes through and it finds the object for you, kind of like a lookup table. And a stub is kind of the location. It's not the object itself, but it's the location where it's loaded. Finds it, loads it up, and then obviously executes the code or links or does whatever it needs to do for it. So think of the stub as kind of a generic kind of term to mean a placeholder or location. So operating systems needed to check if the routine is in the process's memory address space. Dynamic linking is particularly useful for libraries, and then the system also is known as shared libraries. So before the DLLs in Windows, in Unix we had .sos, which was called a shared object. And we have the same process in Unix, actually, Unix and Linux, that uses SO files. So the concept is not new, but it's not new for operating systems in general, although it is on the newer side for Windows. They weren't the originator of the concept. However, the concept itself has been implemented in the form of shared libraries for the longest time. And Java uses shared libraries as well through the RMI. So if you take Java EE programming, you learn about remote method invocation, and you look at that and you go, well, isn't that kind of like DLL loading? Yeah, kind of. But it's across. The only difference with RMI is it's across. So it's remote. So it's across different computers in a more distributed environment. So instead of writing it all on one computer, you load it on multiple computers, and you have the objects located all over the place on different systems. And the RMA manager keeps all of the memory locations together, and it basically resolves the location and tells you where the object is, so you can link to it dynamically. So we have the concept of swapping. So a process can be swapped temporarily out of memory to what's called a backing store, and then brought back into memory for continued execution. So I talked about the backing store actually in the beginning of the lecture. So you take a hard drive, you partition it as a backing store. Well, the operating system is going to do this for you automatically. And then you partition it to look like the main memory, and then you have extra memory. But it's not fast running memory, it's slow running memory. So fast disk large enough to accommodate copies of all of the memory images for a user must provide direct access to these memory images. Well, fast large disk. Well, not necessarily fast. It's still slower than main memory. So what ends up happening is when you install your operating system, people pretty much realize this when they start looking at everything, and they go, well, I have a 300 gigabyte hard drive, and then I only have 280 gigabytes of it available. Well, some of that gigabytes was taken away from you, and it was used for a backing store or for a swap drive. And that's why you have less memory or less disk space available to you as a user, because the operating system has reserved it, has formatted it to be used as a backing store. That's just one of the things it does to your hard drive, but you'll lose space in other ways as well. But that is one of the biggest ways you lose space, though. So what we do is a roll in and a roll out. So swapping rolls something out. We've filled up all of our main memory. No more logical address spaces left. So what do? Well, we have to load something in, but we want it to be loaded simultaneously. So we find something that we're not using or we haven't used in a while, so we could put an aging algorithm on this. And what I'm going to do next week is go through all the different memory management schemes for you. Just like we did with CPU schedulers, we have memory management routines. Very similar to CPU scheduling. We can take a first in, first out, best fit, worst fit, biggest first available spot, last available spot. We can minimize swapping, we can maximize swapping. We can have all these different routines that we go through our algorithms to make maximum use of the memory, which gives us a faster running system, or the experience of a faster running system. So swapping variants are used for a priority-based scheduling. Low priority processes are swapped out so that higher priority processes can be loaded in. Well, the first thing a CPU scheduler is going to do when it loads up the process, in the process control block, we have the address space. So we go to the address space and we go, is that process loaded? Nope. Okay, what's in that space that we need? Swap it out. So we roll it out. We roll it out to the swap drive or the backing store, which is a temporary holding space. Nothing runs from the backing store. In order for the backing store to run, we have to put it back into memory. But if the location is being used and we need it, we take it out. And then we load from the backing store, what is it that we needed? Here it is right here. Put it back in. So we swap things out, we swap things back in, so we have what's needed in memory in order to run the process. And we have multiple processes all using that same logical address space. That is, if we have more processes than we have memory for. In a perfect world, we'd have enough spaces. So if you put more memory on your computer, you have more physical memory, you have less swapping. So the more memory reduces the amount of swapping, makes your system run faster. It does that because then you don't have to swap in and swap out. Swapping in and swapping out is sort of like context switching. Adds time to the processing, makes your CPU run faster, or runs slower, because it's not spending time working with running of the program, it's just spending time swapping. If we have a system that doesn't have enough memory, not enough physical memory, and we have too much stuff loaded up into memory, we have this thing called thrashing that happens. That's when we're trying to load something, but there's no room for it. So we're constantly swapping out, and then what we're swapping out is needed by the program, so we're swapping out, swapping back in, swapping out, swapping back in, swapping out. Nothing's happening, but the hard drive light's on, whole system appears to be running. We have all this stuff going on, but nothing's happening. This is a characteristic of thrashing, essentially, when we're swapping in, constantly swapping and swapping out, but nothing can run because we can't get the whole program into memory at all one time. That only happens these days on systems with very, very low memory, like not enough physical memory. If we have enough physical memory, then we have enough memory to run it, which is actually kind of interesting. So operating systems, they deliver, on the box it says, must have 2 gigs of RAM, must have 4 gigs of RAM. That's what the operating system needs. Your user programs need a lot more than that. So always buy a couple extra gigs when you run, because you need extra space to run your programs with it. And why does the operating system need that? Well, because the kernel's loading stuff up into memory, and it's using that much memory, which is actually not good. I think the current version actually owns like 2 gigs right now or something like that, or 1 gig. Although the RT version of Windows 8 is pretty low. It's like a gig or less at one point, so it made it more efficient. So major parts of the swap time is transfer time, transfer speed, time it takes to actually move something from main memory to a backing store. So the total transfer time is directly proportional to the amount of memory swapped. The more memory that you have swapping, the more it takes to copy it back and forth. So modified versions of swapping are found in many systems, Unix, Linux, Windows. So you can make the swap drive bigger, which means you're going to swap more. You can turn swapping off. If you have a huge memory, you have a system with lots of memory on it, turn or lower your swapping. You probably don't need to swap too much, which means use the memory instead of swapping, essentially, which comes in handy. Essentially, it will speed up your execution. If you have not enough memory, then you have a very low memory allocation, then turn on swapping, and then make swapping half the size of your memory, and then you've basically increased the memory, and so you've made things run faster. What you don't want is a lot of memory with a lot of swapping and a huge swap drive, because then nothing will end up actually getting loaded. It'll all go to the swap drive first. So it'll make your system run a little slower. So what you really want is the main memory. So, and you don't want swapping, because swapping will slow your system down. So Linux maintains a ready queue of ready jobs, and then it has memory images on the disk, and so you can put the queues in memory as well. Well, they have to be in memory. And then you can have the queues themselves. You can swap out the kernel can swap out stuff as well as the user mode. So here's the schematic view of swapping, and here's essentially what's going on. We have the operating system on one side. This is the memory, the main memory, and you have the user space. So the user never gets to touch the kernel space memory that's protected by the kernel. Instead, we have number 1 is swapped out, so process number 1 is on a backing store, and here's a backing store over here. It looks like a disk, since it's meant to be a hard disk. So we take the hard disk and we format it like the main memory, so we can take the processes. And here we have only enough user space for one process in this example, so we take and we swap out process 1 and we swap in process 2. which means we put it from a backing store into the main memory. And so if it's in the main memory, it can run. If it's on the backing store, it can't run. So CPU scheduler comes up. This is a very simplified picture of this. CPU scheduler comes up and says, hey, I want to run process 2, but process 1 is in memory. So we take process number 1 and we take it out. We're just not going to put it back to the disk because that's too slow. If we took it out of memory completely, we'd lose where we are in the processing. Because remember, the CPU schedule, this works directly with CPU scheduling, and remember, we might have already completed half the program already. We might be waiting for the rest of it to complete. But if we take it and we just close it out completely and remove it from memory without putting it on a backing store, then we have to start over from scratch because we have no history of it. Which is why you have everything running on your computer. You turn your computer off, and well, unless you sleep it. If you sleep it, it all gets written to a backing store. It's on the hard drive. It's on a piece of solid state, or not solid, well, it could be solid state, but it's on a piece of memory that's going to be there, which is great. You just swap it all out. So part of your sleep routine says take it all out of main memory, put it in the backing store. Okay, we can go to sleep as long as we want. When we turn the computer back on, it goes from backing store back into memory, and we're back where we were before. When you turn your computer off, nothing stays in main memory, because main memory is logically linked to the physical memory. If there's no power to the physical memory, there's nothing loaded. Which is why you turn your computer off, you lose all that stuff, but you always have what's on your hard drive. So the concept works great for sleeping or hibernation. If you're going to hibernate, if you're going to sleep it, you still have power going to that hard drive. And the hard drive is still spinning. You still have that activity going. If you're going to hibernate it, you're going to write it to the backing store. So the backing store is actually going to store it, and then you're going to turn it all off. You're going to power it all down, and no power is even going. So sleep on is you're still generating a little bit of power from that because you need to get that hard drive active. But the hard drive doesn't take up that much power. It's just a small little piece of hardware on there. And so as long as the hard drive is storing it, you're good. So this particular case is looking at contiguous memory allocation, and we only have 2 processes running. So without any memory management, this is kind of like first come, first serve in terms of CPU scheduling. Contiguous allocation says the main memory usually has 2 partitions in it. One is for the operating system, and the other, which is held in lower memory banks, and then the other one is for the user processes. So in this particular scheme, we have the lower banks, although it looks like the higher banks. I'd turn this upside down, actually. The lower memory banks are going to hold your operating system, which means all your kernel, everything that's loaded by the kernel is going to be loaded there. Why? Because it's faster to run. Your operating system is your foundation. If that's not running fast enough, nothing in the user mode is going to run faster either. So load it, reserve it, don't let the user use it. And then the user's got their own user space. That's going to be in the higher banks. In a contiguous allocation scheme, one gets loaded after the other. You partition it all out, and you go, okay, process 1, process 2, process 3, process 4. You just stack it all up until you run out of memory. And then what happens if a process goes away? Well, it leaves a hole. So that gives you what's called external fragmentation. Because you have a piece of memory that you can't get to. It's available, but maybe it's not big enough, or maybe it's not located together with another piece of memory that you need because you're doing it in a sequential. It's kind of like an array. When you remove something out of an array, well, you have to reorganize the array. Otherwise, you get external fragmentation in that array because you have one location that's empty, and everything else is before or after it. So relocation register is used to protect the user processes from each other, so only one process is accessing the memory, and from changing operating system code and data. So we have the base registers that contain the values. Did I resume this? Yes, I did. Very good. I just was looking at my recording thing. I was like, I wonder if I'm recording this. We had the base register that contains the values of the smallest physical address. And then we have the limit registers that contain the logical addresses for the mapping. So each logical address must be less than the limit address register. So MMU maps everything dynamically. So the operating system goes to the MMU, uses the MMU information. It tells the MMU how to map it. This all happens in real time. Nothing is set, actually. So it depends on our scheme in terms of how we're mapping the memory, in terms of what's actually being stored in the physical locations. So here's a hardware address protection with a base and limit registers that protects the space. What we're talking about is the concept of making only one process available or accessible to a memory location. Mapping it so that process is given this, allocated this space that it has, and it just has the space. No other processes can touch it. If we do that, then we have mutually exclusive processes. We don't have inter-process communication issues with our memory. If we have inter-process communication issues with our memory, we get memory errors. And in the old days, we used to have memory mapping errors. We had the blue screen with all the white characters that come up. We say, memory address such and such. You know, usually it's a mapping error. Like the memory is okay, but the mapping went wrong somehow because one process tried to write into another process space. Happens a lot with viruses, actually. It's an easy way to do a virus is to mess up the memory mapping, actually. Because then if the memory mapping's messed up, nothing's going to run on that system. It just doesn't work. In fact, that's when the whole system stops and the blue screen comes up. And you go, what? Memory corruption. So here's an example where we have the CPU that has an address, has a base and a limit. And then we have this trap to the operating system monitor for addressing error that might come up out of that. So a trap is a user level interrupt that comes down and says, okay, here's your starting, here's your ending, this is mapped to you, we're allocating it, and we're going to use the hardware to support it through the MMU to keep track of which logical address belongs to which one of the processes. And then, lo and behold, here's our physical memory over here. So this is sort of a generic way that the mapping is done. So it's not giving you as much detail as needed. If you were writing your own operating system and you were writing your memory management, you could take an entire course on memory configurations for your operating system, actually. I believe I'm going to save this for next week, actually. Because what I'm going to do is, just like the CPU scheduling, I'm going to go through different scheduling techniques for memory. Because what you're looking at here, just as an example, is contiguous allocation. We can compare contiguous allocation with virtual memory schemes. And we have virtual memory schemes. It's how are you going to allocate, what routine are you going to use to allocate the available memory space? So we have a resource called memory, and memory is allocated to processes. And so we have different algorithms for different memory management schemes that we're going to go through. Some of them contain or will have internal fragmentation, some of them will have external fragmentation, some of them will lead to faster memory allocation, slower memory allocation. Some of them have problems in terms of contiguous versus non-contiguous, and they're solved by implementing concepts like paging, as an example, with page routines. So it brings up a whole slew of different concepts. So today I just wanted to orient you to the concept of memory, main memory, virtual memory, logical memory, physical memory, all the different memory terms and how that fits together, the concept of the mapping that exists. So next week what we'll do, and this goes into our last programming assignment, which is on memory, but you can't really start that yet because I have to give you all of the different memory schemes. So you don't actually have to write a memory manager. I used to have an old assignment that did that, but it's more confusing and harder to simulate than the CPU scheduling. But it's on the same level of CPU scheduling. So CPU scheduling schedules out the processes to get CPU time, while memory management scheduler schedules out the memory to get location time, to get space. It's kind of like a timeshare. It's a timeshare system. So we have one resource that we have to share among multiple processes. We don't have enough of that resource for all of the processes. So then we go through all these different routines to share the memory. So that's memory management in a nutshell. So next week we'll look at contiguous allocation schemes with first come, first serve, best fit, worst fit algorithms. We'll look at fragmentation from an internal, from an external perspective, which is how we're going to measure the efficiency. Because we can't really measure the speed. Then we'll get into the concept of paging and page address translation and page tables that are used to keep track of this stuff in paging hardware. And then we'll look at more examples for the mapping and looking at frames that are used with pages and stuff like that. So someone remind me next week that we need to start on slide 17. And this is a good breaking point actually. So we'll start with contiguous allocation next week. Unless we have questions or comments or concerns from this week. No, you don't have to implement. Do not have to implement a page replacement table or any of these concepts, but you'll have to write a paper, and the paper will compare different memory. But I haven't given you the information for the comparison yet, so we'll go over the last assignment we'll go over next week. So. Questions? No? We're good? Alright, so I'll see you next week. So. Enjoy your registration.